In this video we explain the method of multi-model comparison. With the ILLMO program we promote multi-model comparison over more traditional techniques such as T-tests and analysis of variance, as we think the method is not only much more flexible but in the end also easier to understand and explain. As an example, we use the data that we've used before, which is the spider data. So two conditions: subjects either subjected to the picture of a spider or a real spider, and the measurement is the anxiety felt by the subjects. So once we read in the data, by default ILLMO fits Gaussian distributions to the incoming histograms. And it uses not only Gaussian distributions but also Gaussian distributions with the same standard deviation above both conditions. Now in multi-model comparison, what we're going to do is actually change the model that we apply to the data and systematically analyze which model actually fits best to the data, which is then the preferred description of the data. So one of the options that we have is, rather than having constant variance, we can have variance that depends on the condition. And the way we can see this is we already see it in the distributions, that the distributions have different standard deviation. Another way to show this is to show the condition versus the standard deviation. We see that the standard deviation in the second condition is somewhat higher than in the first condition. Now ILLMO maintains not only the log likelihood criterion, which is shown for both models as the black curve, but it also creates something which is called the Akaike information criterion, or for short, which is actually a measure for the quality of the model, because the model's quality is determined by two aspects: the LLC, which expresses the goodness of fit, but also the number of parameters. So the more parameters you use, obviously, the easier it is to reduce the LLC. So what you see is that by changing the model from constant variance to standard deviation that depends on the condition, the LLC goes down, but only slightly. But the quality is actually, so the AIC actually goes up, which means that the fit becomes worse. Now the way to express this in numbers is to request the maximum likelihood statistics and show that the first model has 3 parameters, because 2 averages and 1 standard deviation, when the second model has 4 parameters, 2 averages and 2 standard deviation, and it finds the LLC, which is slightly higher in case of the simpler model with 3 parameters than in the other case, but the AIC does just the reverse. And there's some tests that actually says that, well, we should actually prefer, as the AIC is smaller, the first model over the second model. Now the theory of multi-model comparison actually says something more. It says that if I know these AICs, I can actually derive the likelihood of each of these models, where I assume that the likelihood of the best model is actually put to 1, and the other ones are a fraction of it. Or other ways stated, it says that the model where the standard deviations are the same is actually 3.5 times as likely as a model where they are different. So that is the outcome of the analysis. We can continue doing this, saying, well, maybe we don't even have to use Gaussian models. We could also have use student distributions. Why would we use student distributions? Because they are kind of less sensitive to outliers than Gaussian distributions, and so which makes them into what is called robust statistics. So we can try that, say, well, replace the distribution, and we see that the AIC indeed goes down by quite a bit. We can again decide whether a bit is really, and you can see that the likelihood ratio, so the evidence ratio, is actually 172, So it means that there's hardly, or otherwise expressed, the probability of the model with a t distribution is 99% and the other one is only half a percent. So there's overwhelming evidence that a model using t distribution is actually better than a model using Gaussian distributions. Now we could expect that probably if we could also try a fourth model that with constant standard deviation, that might actually be even better than the one that we have, which is indeed the case. Again, by reducing number of parameters, the LSC goes up slightly, but that is more than compensated by the fact that it has fewer parameters. So we see that this fourth model is actually the best. Now we can compare all models in a table where we can see the weights, and we see that the weight for the model, for the last model, is actually 78% and only 21% for the model where the standard deviation is. So again, an evidence ratio of about 3 between two models. A traditional statistical test like analysis of variance would test whether the averages are actually, and so we can look at the log likelihood, the condition versus the average. You can see, well, they're kind of similar. So we could also look, for instance, create confidence intervals for them. You can see these are overlapping, so there seems to be some evidence that the averages might actually be very similar. So the way we can test this in ILLMO is say that the private pattern, which has one average per condition, you could change that into a null pattern where the averages are all the same. So again, you see that the LSC goes up by that change, but the AIC stays about the same. So, which probably means that, and another way of looking at this is, we can look at actually the likelihoods, which is the same information as you find here in the table, but now presented as a graph, these weights. You can see that the weights for both models, last models with equal or unequal average, are about the same. So, so there's very little difference between these. We can always compare the last two models in the history, and we can see that the evidence ratio is 1.5, so basically means that